So in this section, we will talk about integrating rational functions, and we're going to see a prescription that will let you integrate basically any kind of rational function. What we'll do is we'll divide this up into a number of special cases and then work towards the general case. And we'll start with rational functions that have linear or quadratic denominators. And then those will be able to solve directly with the techniques that we already know. And then we'll look at a technique called partial fraction expansion that lets you reduce an arbitrary rational function to one of those cases. And here there's going to be a couple of cases to distinguish, depending on whether you have repeated or not repeated factors in the denominator. And we'll finish off with a summary as a prescription of how you can tackle arbitrary rational functions. So just to fix our thoughts, what we want to do here is we want to take the integral of a rational function. So we have a quotient of two polynomials p and q, and we want to compute whatever this quantity is. And what we'll do first of all is we'll distinguish between cases where the degree of p is higher than the degree of q or not. So if the degree of p of x is bigger than or equal to the degree of the denominator, q of x, then the first thing that we'll do is we'll do a Euclidean division. And so if we do our Euclidean division, then we end up with a new polynomial s of x. So this is the quotient, what we formerly called the quotient. And this is, in particular, this is a polynomial. And then you also have a remainder divided by q of x. And here you know that the degree of the remainder is strictly less than the degree of the quotient. And so what that means for the rational function that you're trying to integrate is that you can then reduce it to integrating a polynomial plus integrating the remainder divided by the quotient. And so here, this you know, integral of a polynomial. And then this thing is hopefully simpler. And hopefully it will be true, this will be simpler, this will be something that we can solve using the techniques that we're going to learn. So let's look at an example before moving on. Let's compute the integral of x to the power 3 plus 5x squared plus x plus 6 divided by x squared plus 1 dx. And so at first sight this looks kind of forbidding, but what you have to note is that yes, the degree here is higher than the degree of the denominator, so we're going to do a Euclidean division. I'm going to put that on the side here. So my Euclidean division gives me my numerator and then my denominator, x squared plus 1. So I divide the highest order term by the highest order term. I get x cubed divided by x squared, that's x. Now I multiply back. So I get x cubed and then x times 1, that gives me an x. And now I have to subtract those two things, so I get 0, 5x squared minus 0 times x, and then I lower the 6 plus 6. And now 5x squared divided by x squared, that gives me a 5. And then multiply back, so 5x squared. 5 times 1, that's 5. Nothing in x. Now I subtract, I get 0, 0 times x, and then plus 1. So from this, what I basically get is that my quotient s of x is x plus 5, quotient, and my remainder r of x is just 1. So for my integral, now I can write that as the integral over the quotient plus my remainder divided by the thing that I'm dividing by, x squared plus 1 dx. And so now this is good because integral of x, that's x squared, integral of 5, that's, oh sorry, x squared divided by 2, small mistake there, 5 times x, that's the integral of 5, and then the integral of 1 over x squared plus 1, so this is one that you should definitely know by heart or know how to look up because it comes back over and over again. This is the inverse tangent function. And so finally we end up with x squared divided by 2 plus 5x plus inverse tangent of x plus a constant for the equation. So in this case we were lucky. It was a whole lot simpler. It was something that we could integrate for the remainder. But in general, this won't work without extra tricks that we will cover now. So let's start with a special case. Let's look at the case where the denominator is a linear function. So q is a times x plus b, and we'll assume that a is different from 0. If it's just a constant, then you're back to integrating a polynomial, and we know how to do that. So in this case, our p over q dx becomes very simple because the other thing that we can assume is that the degree of p is less than the degree of q, because if it isn't, do Euclidean division. So here we have that degree of q is 1, and therefore the degree of p has to be 0, otherwise do Euclidean division. So in other words, p of x is a constant which we'll call k for constant. And so now our integral becomes k divided by a times x plus b dx. And so we can write this as k times the integral ax plus b. We can do a substitution. We can call this u, and then du becomes a times dx. And finally, my entire expression becomes k over a du over u. So k over a ln absolute value of u plus my integration constant, and so that's k over a ln absolute value of ax plus b plus my integration constant. I would not recommend that you memorize this rule. I would say if you encounter this case, just do it from scratch. It's a fairly easy case that you can do with substitution. So now we're going to look at the case of a quadratic denominator. So in that case, we have that the degree of the denominator is 2, And that means since the degree of the denominator is always higher than the degree of the numerator, that the degree of p of x has to be 0 or 1. And of course, if the degree is 0, then p of x is just a constant. So let's look at a couple of standard cases, and at the end you'll see that any arbitrary case can be reduced to one of these standard cases by doing a substitution or by completing the square. So we'll start with the case where degree p of x is 1, and in particular we'll take p of x equal to x, and then q of x equal to x squared plus or minus a squared. So in the first case we have the case of x dx divided by x squared plus a squared, and here you can do a substitution. You can take the denominator and call that u, and then d of u is 2 times x dx. And so substituting that back, you get 1/2 du divided by u itself, and that's the substitution we made, and that gives us 1/2 ln of absolute value of u plus c. And then knowing that u is x squared plus a squared, we can back substitute and get ln x squared plus a squared plus the constant. So here, small detail, x squared plus a squared is always positive, so the absolute value signs are not necessary, but we leave them here just to make things uniform with the next case, which is what do you do if you have x dx divided by x squared minus a squared. So the principle is the same. We're going to substitute that by u. So we have u is x squared minus a squared, and then d of u is 2x dx. And so then the integral becomes integral of 1/2 du over u, just as before, and that is 1/2 ln absolute value of u plus c is 1/2 absolute value or logarithm of the absolute value of x squared minus a squared plus c. So here you do need the absolute value signs because x squared minus a squared can become negative. So those are two specific cases. If you have x dx x squared plus a squared or x squared minus a squared. So now let's look at the case where the degree of p of x is 0, so p of x is constant. And in that case we also have two distinct special cases. We have first of all dx x squared plus a squared. That's the easy one. So for that you sort of recognize the inverse tangents from that, and we can make it more concrete as follows. So first of all, I'm going to take out that a squared because it's in the way if I want to make this into the integral that gives me a tangent. So I'll factor out 1 over a squared, and I get dx x over a squared plus 1. Now I can make a small substitution. I can call u x over a, and therefore d of u is dx over a, and my integral becomes 1 over a squared a du u squared plus 1, so that is 1 over a du, u squared plus 1, and that is a form that I recognize, that is the inverse tangent plus a constant, and so therefore I get 1 over a inverse tangent x over a plus c. So that gives me my next form here. And then the last, so let's call this a to stick with the numbering, and then b, the same integral but with a minus sign in the denominator. And here we have no standard expression to do this, but what we can rely on is the fact that the denominator can be factorized. And so in particular we can write 1 over x squared minus a squared as 1 over x minus a x plus a. And so now what we're going to do is we're going to write this as the sum of two individual fractions where you have the factors in the denominator. So something over x minus a plus something over x plus a. And of course now we have to determine what we have to put up in the numerator. So we'll name these just coefficients a and b. And now if I add these two fractions together again, I get a x plus b x minus a times x plus a, and I can collect everything in x, a plus b x, and then plus the rest, a minus b little a, and still x minus a x plus a. And so now if I look at these coefficient expressions here, I have something in x plus a constant term, and if I look back at where I came from, here I basically have 0 times x plus 1. So if I want these two expressions to match, what I need is that a plus b, the coefficient of x, is 0, and a minus b times a is equal to 1. So I want this thing to be 0 and this whole thing to be 1. So this gives me a small system of equations that I can solve. So from this, it's a linear set of equations, I get a is minus b is 1 over 2a. And so now what does that do for us? Well, if I go and I look back at my expansion here, I can substitute these coefficients and I get 1 over 2a x minus a minus 1 over x plus a. And now going back to my original integral, here I can substitute that expansion and I get integral of 1 over 2a and then dx x minus a, and actually let me be a bit quicker here so I can write this as a sum of two integrals dx x minus a minus dx x plus a. And now you see why this is a useful thing to do, this decomposition. Now I have two integrals that I can solve. So this is 1 over 2a times ln x minus a minus ln x plus a plus the integration constant. And one more way that I can write this, so I'm continuing here. Sorry to squeeze everything on one slide. I get 1 over 2a ln of x minus a divided by x plus a plus a constant. Because log of something minus log of something else, that's log of the first thing divided by the second thing. And so that gives me my remaining formula. So here I get log of a rational function, and that's for this integral. So keep in mind that the results are qualitatively very different depending on whether or not you have a plus or a minus. So in one case you get an inverse tan, and in the other case you get a logarithm of a fraction. So this kind of decomposition is called a partial fraction expansion, and will be the subject of the next video. And then just to finish off, now that you have these 4 standard cases, what do you do if you have a general quadratic expression? You just have to complete the square. So for instance, if you have dx x squared plus 4x plus 5, that's not something that we can treat with what we already know, but we can write the denominator as x plus 2 squared plus 1. And now we can make a small substitution. We can call this t, and then our integral becomes dt t squared plus 1. In that case, we're back in case 2a, and we get inverse tangent of t plus a constant, and then we back substitute to get inverse tan x plus 2 plus a constant.